Welcome to the Climate Adaptation Research Symposium, in particular the session on how workers are impacted by and are adapting to extreme heat exposure. It's a very relevant topic and an increasingly relevant topic, unfortunately. Extreme heat exposure is going to be more and more common, and most forecasts of how the climate is going to evolve suggest it will be very common indeed in certain parts of the world within the next decade or so. We've got three first-rate speakers to talk to you about that. Before I introduce the speakers and start the proceedings going, let me just thank all of the people who have made this event possible, the sponsors of the event, all on the screen in front of you right now. And just remind you how to use the tools available to you on the screen. All of the little widgets that you can see in front of you are resizable. Grab the left bottom right-hand corner and to resize them, and you can move them around. Grab the top edge to move them around. You've got a QA icon on your screen. It's a question and answer, obviously. You can click on that and then write in a question for the presenters. Presenters will talk for about 15 to 20 minutes, and then there'll be a few minutes for Q&A after that. So if you have questions for the presenters, please type them into the QA box. I'll see those there, and I'll pick out questions and pass them on to the presenters when we get to the right point. And also there's a question mark icon down there. You can click on that for technical help. Okay, so here are our presenters, Jeff Schrader, Jisung Park, and Hsiang. I feel this is almost like a family event because I'm at Columbia. I'm a professor at the Columbia Business School, and all these guys have very strong connections with Columbia. Jeff Schrader, in fact, is a colleague of mine. Jisung was a student at Columbia. I had the pleasure of teaching him when he was an undergrad. And Sol was a graduate student, of course, at Columbia, and I had the pleasure of dealing with him when he was a graduate student here too. They've all gone on and done great things. Jeff Schrader is talking first, and I'll let Jeff introduce his topic. Jeff, over to you.
All right, thank you very much. I'm Jeff Schrader. I'm at Columbia, as was just mentioned. Today I'm going to be presenting some joint work with Mitch Downey, who's at IIES in Stockholm, and Nels Lind, who's at Emory. And we're looking at the question of how the labor market adjusts to climate change. This is an important topic, and it's a topic that connects with a classic question in climate economics. And that question is, how well can the economy adjust its various factors of production as the climate is changing? And this question is an important one because if the climate changes very fast, or if it's very costly for the economy to adjust its various factors, like the machines it uses, where businesses are located, where employees are employed, then climate change is going to be very costly. In contrast, if factors of production can be adjusted very easily, if the climate changes slowly and predictably, then it might be relatively less costly to adapt to climate change. So as I said, this is a classic question. It's been asked for many decades, or thought about for many decades, specifically in the context of physical capital. So for instance, the machines firms are using. In this paper, we're going to revisit this classic question and ask how well the labor market adjusts to climate change. And we're going to get some empirical estimates on that and then draw implications for climate damages. To do that, we're going to do two things. First, I'll walk through some motivating theory for how we're going to go about trying to estimate adaptability of the labor market to a changing climate. And then we're going to apply the methodology that comes out of that in an empirical setting where we're looking at local labor market responses in the US as it's responding actually to rainfall in our empirical example that I'm going to present today. Well, it's going to have implications for extreme weather events across the board. I'll explain more about why we're empirically looking at rainfall in just a moment. But first, the methodology and the theory. So let's build some intuition for how we're going to go about trying to understand how well the labor market can respond to climate variation. Let's put ourselves in the shoes first of somebody in the construction industry, a worker in the construction industry. And let's assume that if we're in the construction industry, heavy rainfall events, for instance, are a negative productivity shock for us. If it rains, it's just harder for us to work. And let's think about two different possible worlds. One world is a world of costless labor adjustment, meaning that workers can easily, costlessly transition in and out of different sectors. if this is the world we're in, when it rains, workers are lower productivity. They're going to just leave the construction industry, go find a job very easily somewhere else. The costs of that transition are going to be zero because we're assuming costless adjustment, and it's going to happen very quickly. It won't matter, in particular in this world, if the labor market can anticipate upcoming rainfall events. Right when it rains, workers leave, go to another industry. When the rain ends, workers are productive again in construction, they come back to construction. Now let's compare that costless adjustment world to a world with costly adjustment. So you can think about workers paying a cost in terms of needing to search for a new job if they leave the construction industry. You can think about costs on the firm side. Maybe they have to start some paperwork with HR to go about the process of firing a worker, or they need to post a job posting to replace a worker after the rain ends. In this world of costly adjustment, it now matters whether or not the labor market can anticipate upcoming rainfall events. If there's an unanticipated rainfall event, worker productivity might be low. Firms might want to get rid of workers. Workers might want to move to a different sector, but they don't want to pay these adjustment costs to do so. The manager hasn't yet started the paperwork with HR, and so it's going to take some time to do that, fill that paperwork out, and they just haven't gotten started because they were surprised by the rainfall. If rainfall is anticipatable, things are different. Now, say the manager can get the ball rolling on the paperwork. By the time rainfall actually occurs, then the firm can already start shedding their workers when the low productivity event arises. So in a world of costly adjustment, it suddenly matters whether or not the firm and the labor market can anticipate upcoming productivity shocks, upcoming rainfall events. This is going to provide the basis for how we're going to identify empirically the presence of adjustment costs in these local labor markets. We're going to look at employment responses to more or less anticipatable rainfall events. If there's a different employment response to more versus less anticipatable rainfall, then that's evidence for costly adjustment. We're going to apply this conceptual model empirically to local labor markets in the US using a variety of data sources. The first is information on employment. We're going to get that from the Quarterly Census of Employment and Wages, the QCEW. This is a fantastic data product that comes from unemployment insurance records. It gives you monthly information on employment in a bunch of different sectors in the United States at the county level. The one caveat for this talk is that it does not record well employment in the agricultural sector. So I won't talk about agricultural employment if folks have a question about that, but we will talk about all other sectors in the US. We're going to take those data, we're going to aggregate them from the county level up to the commuting zone level. So we're going to look at 720 commuting zones. Commuting zones are just collections of counties that are constructed to capture local commuting patterns and therefore capture local labor markets. We're also going to aggregate industrial scale employment up to 4 sectors. We're going to look at construction, real estate, services, and trade. So services like education, traded like manufacturing. And we're going to look at the period from 1990 to 2016. We're going to combine that employment data with information on the weather. So we're going to be looking at precipitation. We're also going to control for temperature in our analysis. These pieces of data are going to come from PRISM, a standard gridded data product that we're then going to aggregate up to the commuting zone level, where we population weight the spatial aggregations. We have monthly population weighted precipitation and temperature for each commuting zone. The final piece we need is some way to affect the anticipatability or the forecastability of weather events. Because again, we're looking to see whether or not employment changes vary as the amount of anticipatability of rainfall changes. To vary the forecastability of rainfall, we're going to use one of my personal favorite climate phenomena, and I think a favorite of some other people on this panel, El Nino Southern Oscillation. El Nino Southern Oscillation, or ENSO, is often in the news these days, so I think many of us are familiar with it. But if you aren't, you can think of it as a climate phenomenon in the equatorial Pacific Ocean that involves, among other things, periodic warming and cooling of equatorial Pacific waters. This is an important climate phenomenon for a number of reasons. One, because it affects weather patterns all over the world. And in particular, it has a very strong effect on precipitation in the United States. Because of its strong effect on precipitation in the US, we, as well as other weather forecasters, can use changes in El Nino Southern Oscillation to predict rainfall in the United States. And it's particularly informative for rainfall rather than temperature, motivating in part our focus on rainfall in this talk. So we're going to use El Nino Southern Oscillation to construct monthly forecasts of rainfall across the continental US. And we're going to exploit differences in forecastability in different areas of the US to understand how employment responses vary as anticipatability of rainfall varies. Tying all this together, we end up with one big estimating strategy. This is a complicated looking set of functions, but it boils down to something actually pretty simple. We're going to be doing instrumental variables, local projection to estimate impulse responses of employment to more or less forecastable rainfall. What that means is that we're basically going to do two things. We're going to first forecast rainfall using El Nino Southern Oscillation. So the first stage that I've indicated here, the important parts, the most important parts are that we are taking rainfall, the log of rainfall for each commuting zone C in month T, and we're predicting it using El Nino Southern Oscillation at time T minus L. So we're constructing L period ahead forecasts of rainfall using El Nino Southern Oscillation. And in particular, we're constructing those forecasts separately for each commuting zone. So for each commuting zone, it's all happening in one estimation step, but each commuting zone gets its own forecast based on the effect that El Nino Southern Oscillation has on rainfall in that commuting zone, because we're interacting El Nino Southern Oscillation with commuting zone fixed effects. And so all the rest of the stuff in this first stage equation are controls. The important point is that we're forecasting rainfall at time T using El Nino Southern Oscillation at time T minus L, and each commuting zone is getting its own forecast. We have controls for time, so month, commuting zone by month of year to account for seasonality, longer lags of El Nino Southern Oscillation to account for autocorrelation in that process, lags of rainfall, lags of temperature, lags of employment, a number of controls, some of which are important for this first stage, some of which are important for the second stage. In the second step, the second stage, we then take these rainfall forecasts and we look at how they affect employment. Right, so the important part of the second stage is that we're looking at how employment in commuting zone C at time T plus H, so employment in the future, is affected by rainfall forecasts given to us by our first stage. Otherwise, all of the covariates in the second stage are the same as the first stage because, again, this is an instrumental variables local projection method. And as the conceptual model indicated, what we're looking for here is how employment responds to rainfall forecasts at different horizons. If there are differences in those employment responses, that's evidence for adjustment costs. If all of the responses are the same, then that's evidence that we're in a world of costless adjustment. So now let's turn to results. We're going to start by looking at this first stage forecasting rainfall using El Nino Southern Oscillation. I'm going to show this in a couple of ways. First, I'm going to show you a map of the coefficients on El Nino Southern Oscillation in the first stage. And I'm showing you that for two different forecasting horizons, the 1 month horizon on the left and the 6 month horizon on the right. We're doing the forecasts from 0 all the way out to 6 months. So this is just a sample of the forecast that we've constructed. You can see that broadly speaking, El Nino, a warmer, say, water in the equatorial Pacific forecasts lower rainfall across northern latitudes in the US, heavier rainfall across the southern latitudes of the US, with particularly strong effects in California, the Southwest, Texas, the Southeast, and the Mountain West. These patterns are fairly consistent across 0 and 6 month, or 1 and 6 month horizon forecasts, but there are some differences at different horizons. These differences are going to allow us to tease out effects in areas that have longer anticipation horizons that get more warning about upcoming rainfall versus areas that get just a shorter warning about upcoming rainfall. So this is the first stage, how the first stage coefficients look. You can also think about what type of rainfall El Nino Southern Oscillation predicts in a time series way. I won't dwell on this figure, but basically it's saying that if El Nino Southern Oscillation predicts heavier rainfall in an area, it's predicting heavier rainfall for the next few months. So in your mind, you should think of a 3, 4, or 5 month period of heavier rainfall in a place like Texas when El Nino Southern Oscillation is higher. Just a few more statistics about the quality of this. So in brief, El Nino Southern Oscillation is a quite good predictor of rainfall in the US. About 8% of all rainfall variability, deseasonalized rainfall variability in the US is explained by El Nino Southern Oscillation. So it's a major component of monthly scale rainfall variation in the United States. You can assess that statistically in a variety of ways, And essentially, the punchline is El Nino is a quite good predictor. This is one of the main reasons why weather forecasters use it so often to construct their seasonal or long-run weather forecasts. So now we know that we can use El Nino Southern Oscillation to get variation in the anticipatability of rainfall in different commuting zones in the US. Now we're going to look and see how those rainfall forecasts affect employment as we vary the forecast horizon. I'm going to show you that in a variety of figures. Each of these figures is constructed from the regressions that I described a moment ago. We're going to start with the 0-month horizon forecast. This is the forecast of rainfall when the forecast arrives in the same month as rainfall arrives. You can think of this as kind of the effect of unanticipatable rainfall. The x-axis is showing you time from when rainfall arrives. So 0 is the month when rainfall arrives. Positive numbers are months after rainfall arrives. Negative numbers are months before. The y-axis is the elasticity of employment with respect to rainfall. So it's telling you just how employment changes as rainfall increases. And the blue line is showing you that when the construction labor market is hit by an unanticipated rainfall event, in the month when the rainfall occurs, there's a small, but very small drop in employment, and employment continues to drop for the next few months as this negative productivity shock works its way through the local labor market. The shaded area is a 95% confidence band. You can see that this is a significant, but I'll emphasize a small effect on employment. Now let's see what happens as we increase the length of time that the market has to respond, as we increase the forecast horizon. So we're going to remove confidence bands for legibility and see what happens with the 0-month horizon forecast, 1-month horizon, 2-month horizon, 3-month horizon forecast. So all we're doing here is extending the amount of time the market has to respond to upcoming rainfall events. We're expanding the amount of anticipatability of these rainfall events empirically. And you can see a few important things. One, the market starts to respond earlier and earlier. In fact, it starts to respond as soon as news about upcoming rainfall events arrives. So at 3 months, for instance, the market is responding in advance of, the 3-month horizon forecast, the market is responding in advance of the actual realization of rainfall. Second, at the time when rainfall occurs, the response of employment is stronger and stronger and stronger. This is because the market has been able to start some of these processes going so that when the actual negative productivity shock arrives, the employment can move more away from the negatively affected sector, in this case, construction. So that's for 3-month horizon forecast. Let's go out a few more months. 4-month horizon, 5 and 6-month horizon. Again, stronger and stronger effect when the rainfall actually arrives, earlier and earlier beginning to the response. We can put confidence intervals back on that and just see that there is a significantly different, statistically significant difference between the 6 and 0-month horizon forecast, for instance. But also more practically, it's about a 6 times bigger effect at 6-month horizon versus 0-month horizon forecast. This is telling us that adjustment costs are large in this setting, right? If this was a costless adjustment setting for the labor market, we would see all of these impulse responses lying on top of each other. Instead, these impulse responses are spread out from each other. This is indicative of costly adjustment here. We can look at the other sectors. Construction is reproduced on the bottom right. Real estate has a small decline in employment. We interpret this as coming from reductions in output from the construction sector. Real estate largely employs construction as an intermediate input. Traded and services, very little is going on. This is consistent with other evidence that these sectors are fairly insulated from this particular type of shock. If anything, they might see modest increases as they're absorbing workers from the construction sector. Putting all this together, we can think about what our empirical results imply for the size of adjustment costs in the US, and then we can start to draw some conclusions for welfare impacts from climate change or other impacts from climate change. In the paper, we go through the construction and fitting of a big model. It's outside the scope of this presentation, but in essence, we treat each commuting zone as a small open economy, and we're thinking about adjustment costs within the labor market in that economy as arising because of transition between sectors. So a worker starts each period in a sector, they can pay some cost to move sectors, but they might want to do that if they think that their productivity or wages are going to be higher in that other sector. We can fit the model to our empirical results and get a sense for the size of the adjustment costs. To do that, or to get some intuition for that, focus on the leftmost 2 columns in this figure. There's a lot going on in the figure, but let's just look at the leftmost 2 columns. So in the baseline column, this is our model fit to the empirical results we saw. Construction has a big negative drop, but it's differential across forecasting horizon. Real estate has a modest decline coming from knock-on effects from a drop in construction output. Services and traded sector have slight increases. Compare that to what our model would predict if we were in a low labor adjustment cost world. In that case, as I mentioned before, all of the impulse responses would lie right on top of each other. There's no benefit of anticipating upcoming rainfall events. And moreover, the overall shock is smaller. That's because as the economy can easily adjust to these types of shocks, these types of productivity losses, there aren't knock-on effects on other sectors, and the overall size of the effect is reduced. Given that the model is better fit to the leftmost column, this is one way, or you can get some intuition for the fact that the model is telling us that we're in a large adjustment cost setting. And in fact, we can use the model to get some numerical quantities for that. This has some immediate consequences for climate change. This is where I'll conclude. One is just what I started with at the beginning. We're in a high adjustment cost world. That means that as the climate is changing, we're going to be paying adjustment costs every time the climate changes. That's going to have welfare consequences. Second, one of the important implications for climate change for precipitation is that there's going to be increased volatility of precipitation. Predictions are 30% increased volatility of precipitation in the United States. We're going to have to pay adjustment costs for that as well. Both these costs need to be taken into account when we're thinking about future damages from climate change. Thanks.
Okay, thanks very much indeed, Jeff. That was a fascinating paper. Very clever presentation, clever strategy too. Can I ask you a quick question? I mean, you showed that there was an increase in employment in services and in traded goods, I think it was, in that last slide.
That's right.
What's the explanation there exactly?
So those results are coming to us. I mean, in part, we get that empirically, we get these small increases, but in the model, that comes because those sectors they have two effects. One, they're being hit negatively by the fact that they use some construction output. So that could mean that they would see declines. The fact that we see increases empirically means that that effect is being dominated by the fact that they're now absorbing some output from, or some workers from construction. And for instance, the traded sector in particular, it's not experiencing any loss in demand locally because its demand is coming from outside. So it can easily expand its worker base on the cheap now, right? Because they're absorbing construction workers. So they experience some increase. And then some parts of the services sector are also tradable, so they experience a similar increase.
But I mean, services sector includes, for example, tourism. Like what you'd expect to be negatively affected by a sort of rainfall, right?
Right. Yeah. So empirically, we don't find that to be the case, right? But there's a lot in the services sector. Tourism is a fairly small part of the sector for most of the U.S. So I imagine that if we went and looked in places where tourism is a bigger part of the economy, we might find very different effects. But the overall services sector, right, is dominated by other things, service workers in restaurants, for instance.
Right, yeah. Jisung, Sol, do you have any questions for Jeff?
No, I think.
Right, okay, very good.
We'll just go straight to the audience.
Yeah, I don't see any questions from the audience actually at this point. So let's go on to the next presenter, Jisung. So let me click on the next slide, and that's Jisung Park, next speaker, who is an assistant professor at UCLA in the Public Policy School. So Jisung, over to you.
Great. So yeah, Jeff, thank you for moderating it. And Jeff, that was a fascinating presentation. So once again, my name is Jisung Park, assistant professor in public policy here at UCLA, and also the associate director for economic research at the Luskin Center. I'll be presenting a joint project with Nora Pankratz, who is a postdoc with us, and Patrick Baer, who's at Stanford. And I'll also be talking about adaptation to climate change in the labor market, but focusing in particular on workplace safety and how extreme heat may affect workplace safety. All right, but let me start with a more general observation that exposure to what economists might call environmental externalities on the job, whether that's air pollution or extreme temperature due to climate change, is a remarkably widespread phenomenon. Globally, there are upwards of 1.2 billion individuals working in agriculture and construction alone. And even in the United States, over 2/3 of the roughly 100 million or so workers without a bachelor's degree report routine exposure to harsh environmental conditions on the job. This is actually including in many indoor occupations. And we may be concerned about what extreme heat may mean for these workers in particular, given the fact that so much of the world is expected to experience so much more of it over the coming decades. And this is where the mapping from mean shift in global climate to manifestation of local extreme temperatures is highly uneven, which means that there are some parts of the world that are expected to experience over 150 additional days per year above 90 by 2050 alone, even with relatively aggressive mitigation scenarios. So we might want to understand what this means for various labor outcomes. But as Jeff alluded to, trying to understand adaptation in the labor market is non-trivially challenging. Part of this is because labor is inherently a two-way tied transaction, right? You've got profit maximizing firms and utility maximizing workers implicitly bargaining not only for wages and employment, but also for a range of workplace amenities, of which workplace safety is often an important component, especially for workers at the lower end of the skills distribution. So in this paper, we're going to try to build on existing work by focusing on the potential effect of extreme temperature on worker safety and health, and really using that as a prism through which we might better understand the process of adaptation in the labor market, and specifically the potential for labor market frictions of various kinds to affect the process of adaptation investment. And I'll tell you more about what I mean by that in a moment. Last piece of motivation, whether or not there's clear guidance from the academic literature, policymakers around the world seem increasingly pressured or interested to enact what you might call de facto adaptation policy through the labor market. This could be through some version of the Green New Deal, or in California, workplace heat safety mandates, which we'll be talking about in more detail in this presentation, or in the case of China, heat-related labor subsidies. Now, what these kinds of effects mean for either economic efficiency or distributional equity remains relatively understudied, and this is we believe, an important research agenda that hopefully this project can begin to contribute to. Okay, so that's the motivation. Here's what we're trying to do in this paper. We'll be using a unique confidential claims level data set of workers' compensation injury claims from the universe of California's working compensation system over a roughly 20-year period, linked to daily weather data at the zip code level to do a number of things. First, we're going to try to assess what is the causal impact of extreme temperature, in particular extreme heat, on local same-day injury risk. And we're going to try to do so while being mindful of potential endogenous changes in labor inputs, right? How heat may affect labor demand or supply. Second, we're going to try to look under the hood and see if we can say anything about mechanisms. And here we're going to leverage the richness of the administrative data set and really try to focus, based on a simple model we're going to write down, on whether costs of adaptation or costs of safety investment, including potentially non-pecuniary costs, may play a role in mediating the temperature safety relationship. And then finally, we're going to exploit the fact that California in 2006 became the first state to implement what was then the first mandated workplace adaptation standard, to see what effect that kind of policy might have on this relationship. So we're not the first to think about the effect of temperature on labor-related outcomes, nor are we the first to think about adaptation to climate change or the welfare consequences of labor market policies generally. We believe we are among the first to study these questions in combination, and to our knowledge, the first to empirically evaluate a directed adaptation policy in the labor market. But if we're missing important citations, please let us know. And before I tell you about the data and the empirical strategy, let me just spend a couple of minutes on the intellectual scaffolding that's going to guide our empirical analysis. In the paper, we write down a simple economic model of workplace safety investment. I'm just going to summarize the empirically relevant bits here. The key point is that we're thinking of workplace safety risk, R, as both a function of, let's call it, direct physiological risk due to extreme temperature. There's a wealth of evidence that suggests that extreme heat affects both cognitive and physical functioning in adverse ways, as well as just health generally. But risk also depends on this S term, which is we're going to think of as endogenous safety investments or adaptation responses that either firms or workers may engage in response to changes in weather conditions, here in particular, extreme temperature. And the point here to stress, right, is that even if we're able to identify a causally well-identified reduced form effect of temperature on injuries, this is almost always going to reflect a combination of these two potential factors, right? Another implication of the model is going to be that under a fairly reasonable set of assumptions, you'd actually expect hotter temperature to increase residual realized injuries on the job, not only in obviously exposed settings like outdoor construction work or agricultural production, but also in indoor settings. And this is true basically as long as extreme heat has a non-negative effect on the marginal cost of providing a given level of safety or on labor productivity. So as an example, if you're in a manufacturing plant and 95-degree day raises the cost of maintaining a given room temperature because you have to run the AC or ceiling fans, that in a competitive market setting, we would expect that to lead optimizing firms to reduce the overall realized level of workplace safety, which would result in some kind of residual injury risk, which is what we're going to try to test for. The model also predicts that you would expect to see temperature affect not only heat illnesses such as heat exhaustion or heat stroke, but also a wide range of injuries, especially in settings where the work is just baseline quite dangerous. And that if you believe workplace safety is a normal good, which the empirical evidence suggests it is, then you would expect larger, more positive effects of extreme temperature on injury risk for lower total compensation or lower skilled workers. Another upshot of this way of thinking about adaptation is that as long as the costs of implementing a given adaptation technology are non-zero, you might want to think about these costs. So in other words, technical feasibility is a necessary but insufficient condition for adaptation. And one might be particularly concerned about the possibility that costs in this setting are not just pecuniary and private in nature. That is, they may include costs associated with things like overcoming collective action problems, information problems, or various other labor market frictions. And so while we're not going to be able to answer these questions definitively, we think it's important to raise this general question about what kinds of adaptation investments do we expect to see in a world with such frictions? And here we're focusing on labor market frictions, and without. And this is along the lines of Jeff's presentation as well. Okay. So we're going to operationalize this using confidential claims level data from the California Division of Labor. We're going to link this information, these injury claims, to daily weather data from the PRISM model at the zip code day level. And we're also going to augment the analysis with a range of other labor outcomes, including firm operating costs from CompuStat, employment from QCEW, and weekly hours worked from the current population survey. And here's the main identifying equation. So most of the results that I'm going to show you are some variation of this theme. We're regressing some transformation of the number of injuries reported as occurring in a given zip code on a given day on a vector of temperature bins, right, ranging from high temperature below 40 degrees Fahrenheit to above 105, a vector of precipitation bins, again at the zip code day level. And the main action, so to speak, in terms of identification is going to come from this eta term, the zip code by month fixed effect, and this gamma term, a month-year fixed effect. So you can think of this as trying to net out location or zip code specific seasonality in working patterns, as well as statewide shocks at the month-year level or trends at that level as well. One way to think about the identification strategy is just visually here, right? We're leveraging day-to-day variation in temperature within a given zip code over time. And I should say the results, the main results are robust to including day-of-month fixed effects as well, if you're concerned about the, the trend within a given month of daily temperature. So here's the main effect. This is showing the effect of being in a day with temperature in any one of these temperature bins on the x-axis on the relative number of injuries in a given zip code day relative to a day with high temperatures in the low 60s. And I apologize, this is actually an earlier version of the regression run. We weren't able to get the latest off of the secure server in time. But the point to stress is that hotter temperatures appear to be associated with higher injury rates. And the magnitude across a range of specifications is somewhere on the order of a 95-degree day, increasing this propensity by around 6 to 9%, depending on whether we use an IHS or a Poisson or something else. Okay. This effect is robust to a variety of robustness checks, for instance, including the possibility that there's spurious correlation in terms of warming patterns and injury patterns at the county level. So it's robust to the inclusion of such trends, to including leads and lags in daily temperature. And it's also the significance of the effect is robust to alternative sensible clustering of standard errors. But one important potential concern with this strategy, especially given what Jeff just presented and what I imagine Sol is about to present after this, is the concern that demand for labor inputs may itself be a function of extreme temperature at the daily level. In particular, if hotter temperature leads, for whatever reason, to increased daily labor demand, if for whatever reason most of us behave like ice cream vendors, then the estimate that we just presented in terms of the effect of temperature on injuries may be overstated, may be upward bias. If, on the other hand, in general, hotter temperature, extreme heat anyway, leads to a reduction in labor inputs, as has been found in the case of Grefsiv and Nidell, for example, then our estimates, with a few caveats about selection on worker type aside, are more likely to be understated in terms of the magnitude. So that's our prior going in. But to try to further address this concern, we use occupation by MSA week data on hours worked and industry by quarter employment data from the QCW to try to see what is the relationship between extreme heat and employment on either the extensive or intensive margin. With a few interesting exceptions, we find that on the whole, extreme heat seems to lower employment at hours, which makes us a little bit more confident that the effects that we're identifying are probably not grossly overstated. Okay, so now let me see if I can talk a little bit about potential mechanisms. And again, as I mentioned earlier, if you think that extreme temperature affects either labor productivity or the cost of providing a given level of safety, there are a number of predictions that follow. You would expect injuries to spike on hotter days, not only outdoors, but also indoors, in indoor production settings, not only for heat, obviously heat-related illnesses, but also for other types of injuries, like falling off of a ladder or dropping hot chemicals on yourself, as well as to be more pronounced in settings that employ lower wage workers. And this is indeed, by and large, what we seem to find. So not only do we find this relationship between hotter temperature and injuries in outdoor sectors like agriculture, construction, and utilities, as shown here, but we also find a significant effect of hotter temperature on injuries in manufacturing, in wholesale trade, and in transportation and warehousing. which typically involve workers working indoors. Right? We also see, maybe not surprisingly, that injuries or claims, I should say, that are tagged as being caused by extreme temperature, at least in the official records, these spike on hotter days. Other types of claims seem to increase on hotter days as well. So again, falling from a high place, being stuck between moving objects, etc. Another way to look at this is to limit the analysis to split the analysis in terms of injuries that involve core internal organs, which you may think are more likely to be due to heat exhaustion, right, or direct heat exposure. Yes, we see a relationship there, but we also see a relationship between heat and injuries that involve outer extremities, so losing an arm or an ear, or etc. This is why I don't talk about my research over dinner. And then finally, while this sort of aggregated industry level classification can only tell us so much, we don't find significant evidence of extreme heat affecting injury risk in industries such as management, finance, and insurance or information, which typically tend to employ higher total compensation workers, although there are some exceptions to this trend, namely utilities, which has high wage workers and also a pretty strong temperature injury response function. One immediate potential policy implication of this is that official records or official statistics of heat-related workplace safety risk may be understated. So in California, the official record suggests that there are around 850 heat-related injuries and illnesses per year. Our estimates suggest that that number, if you include all these other types of injuries, is more like 4,200. That's worth comparing to recent estimates of the heat-related injury burden in the entire United States being estimated around 4,000 a year. Right? Okay, in the few minutes I have left, let me talk about the third part of the paper, which is I think, an exciting part of the paper, which has to do with adaptation policy. So in 2006, California became the first state to adopt a mandatory workplace heat standard. It was essentially an information intervention as well as a technology standard. So it involved a vigorous sort of public awareness education campaign around heat-related various safety risks on the job, as well as for industries that have outdoor workers, a mandatory training system, a buddy system, and what are called high heat protocols that kick in when the temperature is expected to be 95 or above, that require firms to provide free water, shade, and mandatory rest breaks of 5 minutes per hour. Somewhat unusually, it was coupled with a vigorous enforcement regime, with Cal OSHA conducting over 18,000 citations for this standard alone in the ensuing years. And so while the variation in this policy is not quite experimental, we're going to try to see if we can assess to what extent this policy did or did not affect the heat injury relationship that it was meant to try to affect. So we look at this a number of ways. This is the clearest way, I think, of looking at it. It's showing the earlier main effect, right, in terms of the temperature's effect on injury risk. But prior to 2006 in the light blue coefficients, and post-2006 in the Navy. And if you can read, the p-values are showing the significance of the difference between those point estimates. And again, only so much we can say in terms of interpreting this, but very clearly, right, there's more action in terms of difference in those coefficients at the higher end of the temperature distribution. Not much else seems to be changing at other points of the temperature distribution. Another way to look at that is to estimate the top end coefficient, the high heat coefficients, separately by year, and to plot them as we've done here. And again, something seems to be changing around 2006. Now, that may be due to correlated other changes in other policies or economic conditions. We can't say for sure, but this is certainly consistent with the policy having had some benefit in terms of reducing heat-related safety risk. going to skip that. An important point to note here, though, is how we interpret the welfare consequences of such a policy depend crucially on the composition of costs. And what I mean by that here is you can imagine a world where most adaptation costs, at least in terms of workplace safety with respect to heat, are private pecuniary costs that workers and firms bear. And you'd expect in that case firms to pass on some of these costs to workers in terms of employment and wages. And or you can imagine a world where some proportion of those costs comprise things like overcoming, again, collective action problems, information problems, or other frictions and market failures in adaptation investment, in which case you could expect, or at least anticipate, the policy to possibly have a welfare enhancing effect. We're not going to be able to answer these questions definitively, but we find at least some suggestive evidence that it may not have only been the former. So when we look at, for example, the universe of publicly listed firms using CompuStat and their operating expenses, and using a triple difference strategy that basically looks at California versus non-California based firms, pre-post policy, and regulated versus unregulated firms, we find no evidence that this led to significant discernible changes in costs. And we're currently working on what this policy may have done to how firms hire and retain workers, especially on hotter days. So let me wrap up by just recapping the preliminary findings so far in this study. We find that hotter temperature appears to exert a significant and positive causal impact on workplace injuries. We find evidence also consistent with hotter temperature in the workplace effectively raising the cost of safety provision, which is consistent with a model of heat on the job as a workplace disamenity. And our estimates also suggest that official statistics may grossly understate heat-related safety risks. And third, we find that many of these injuries appear to have been preventable, but for whatever reasons that are as yet unclear, they do not seem to have investments in such safety investments do not seem to have occurred in private equilibrium. And so we think that this may have implications for how we think about active adaptation policy in the labor market that may or may not have the potential to sort of get us closer to the Pareto adaptation frontier, so to speak. And I'll stop there.
Okay, thanks very much indeed, Jisung. Very interesting. I had a question myself, and there's a couple of questions in the Q&A. For something like agriculture or other outside activities, I mean, a classic response to really high temperatures is to change the hours of work so that you start working earlier in the morning when it's cooler and things like that. And that's been a classic in a lot of really high temperature countries. Do you see any evidence of that at all in California, or is that just not something you've got data on?
No, that's a great point, Jeff. And we unfortunately don't have the data to look at that. Anecdotally, I've heard that to be true. We would need data right on when workers come in and when workers leave. But you would imagine if that's going on, whatever we observe, it would be net of that kind of a strategy, because that's like the lowest cost way of adapting to this.
Yeah. Okay, so let me just read you some of the questions which we popped up in the Q&A. First one is, what's the reason behind workplace injuries mostly increasing with warmer temperatures here versus the classic U-shaped curve showing that mortality increases anomalously with hot and cold temperatures?
Right. No, that's a great question. It's something we've puzzled about a lot. There's the U-shaped relationship in terms of mortality. There's actually another paper by Marcus Dillander who finds a U-shaped relationship in terms of injuries. Our best guess so far is that California, just given the mild climate that it is, relatively mild anyway in terms of cold, just doesn't seem to experience that many very cold days, days that are cold enough, I guess, to lead to injuries, workplace injuries. But I will admit that is a puzzle, at least in terms of our findings so far.
Right. Another question is, are you able to distinguish injuries that stem from violent incidents? I think in principle we are. There is a category of
of claims that has to do with workplace violence, I guess. We haven't tried that. That's an interesting suggestion.
Yeah, right. I mean, some of Sol's work suggests that high temperatures provoke violent behavior, right?
That's right.
So,
that's right.
Yeah. And the final question is, have you looked at hours spent outdoors?
So if I'm understanding the question correctly, so first of all, we don't unfortunately have data that specifically outlines whether someone was outdoors or indoors, at least in terms of what we've analyzed so far. I wish we could ask the audience member to elaborate on the question.
Yeah.
I don't know if we have that technical feasibility.
I don't think we do. I don't think we have the time either, unfortunately, actually. I'm watching the seconds click by here. So anyway, let me thank you very much indeed for that presentation, Jisung, and move on to Sol. So Sol Hsiang next.
Jisung, thank you for doing that. I think that was excellent, careful work, and it's a question I've wondered about myself for a very long time. So I'm glad to see someone's doing this very carefully. What I'll try to cover in the next, very briskly in the next 20 minutes, is some work done jointly with the members of the Climate Impact Lab, which is a multi-university, multi-institution research consortium trying to understand the global social cost of carbon. As many of you are aware, we are using a variety of different economic models in for regulatory purposes. Many of these models were not designed for regulation. And in the work, sort of in going through what's underlying these models, there's very little empirical foundation in terms of how they've been assembled and which leads to the question of whether we're regulating the economy based on the best available empirical evidence. As we have gone and looked into the literature, there is, as exemplified by the two other speakers here, a growing body of really excellent research that is not making its way into regulation. So one goal of the Climate Impact Lab is to really take the best available evidence that's out there and bring it into the types of damage functions and modeling exercises used to design regulations reflecting the social cost of carbon. And in doing that exercise, it's also very important that damages around the world are very well represented. In many of the previous studies, just a handful of cities have been analyzed, often from very wealthy countries. And we think it's quite important that low-income populations are represented. And then also, as Jisung and Jeff were describing, it's really important that we reflect the costs and benefits of adaptation when we think about what is coming down the road here. So the overall agenda of the Climate Impact Lab is to go through a whole variety of different sectors of the global economy and trying to one by one elucidate what is going on and what we might expect in terms of climate change. Today, what I'm going to focus on is just the effect of labor. That's the session we're in. And so here is we've known for quite some time that thermal conditions influence the productivity of individuals. So here's one of my favorite studies in 47, Charles Mackworth, got a bunch of guys in the military to do arm curls until they collapsed from exhaustion. The graph on the right is showing the results from that particular study. As the temperature got higher, they were doing fewer and fewer arm curls. And so this has kind of been something we've known about for some time, but thinking through what the social costs are has been challenging. The particular study I'm showing you right now is one in which we are actually thinking about how much less happy the global workforce will be having to work in an environment that has been altered by climate change. So you can think of this as we're trying to price the immiseration of the global workforce by turning up the temperature everywhere. And so many people, as have been discussed, are working in exposed environments, and presumably they're going to have to continue working despite rising temperatures. So the simple economic framework we're going to live in is a world in which firms are going to maximize profits, workers are going to choose how much labor to supply, and wages are going to be set competitively. The picture for this environment is sort of just simple equilibrium in a market where we have a supply of workers, demand for workers. And you can think of there being two different effects of rising temperatures. The one that has been discussed a lot in previous literature is the fact that productivity is going to decline when the temperature rises. And so presumably for each individual hour of work, less output is produced. The other fact that we are focusing on here is the fact that workers experience a higher disutility of working in hotter thermal environments or in some thermal environments. Now, to think through the shift in the equilibrium from the optimum to some change in the future, you can think about there being price changes, changes in wages, and changes in the supply of labor. It turns out that the incidence of these two changes can be partitioned between the worker's utility and the firm's profits. And any changes in wages actually just operate as a transfer because it just changes the allocation of surplus between workers and firms. So thinking about the two remaining terms, the overall change in output and the change in utility, previous work has really focused a lot on how much less work we get out of the workers, like what is marginal product times the time that they're working. So previous work has really tried to catalog this, and that's not what we're going to focus on here. Other studies have also looked at the overall productivity of the entire economy, which captures these two shaded regions. What we are doing here is trying to understand the shaded area under that curve, describing how unhappy workers are when they're supplying their labor, the disutility of working. And the key insight is to recognize that if we observe workers are quitting early, right? They're working fewer hours on a hot day. That is an indicator that they are unhappy, not just during those few minutes when they quit, but in all of the time that they're working up until that quitting moment. And so we are going to use information just about how workers are changing their behavior through those few marginal minutes to infer something about their disutility throughout the entire day. Now, to do that, there's an empirical exercise behind it. So we actually scoured basically the internet, trying to understand where we can get information of how workers allocate their time. We collect a sample that represents roughly a third of the global population across several countries that in an effort to be as representative as possible. And they are all primarily from the 21st century. To give you a sense, this is what the kind of data looks like. So we are using time use surveys in which workers are reporting everything they do for every few minutes of the day. Here's just an excerpt from one of them. And we're going to focus on this blue chunk at the very top, which is looking at how much individual workers are working in 24-hour cycles. Now, following on previous work by folks on the call, I'm sure folks in the audience, we're going to think about workers as living in basically one of two possible industries. We'll talk about the high risk, sets of industries. There's a high risk group that are exposed to outdoor environments throughout a large fraction of their workday. And there's low risk populations that are individuals, perhaps like many of us, who work indoors and are able to protect ourselves from outdoor temperatures to some extent. We also collect a variety of other types of climate data, and we're going to use some information for projections, including satellite data, but I won't get into the details here. We run a fairly standard panel regression model, or sort of a pseudo panel, because in many cases we don't observe the same worker many times, but we observe workers who are resampled from the same locations. And the goal is to really isolate the effect of thermal conditions on the minutes of labor supplied. In this very large global regression, these are the main results. These are the response functions. This is the main result of the empirical exercise. So on the left, you see that as temperatures increase, among high-risk workers, there's a peak, and at a very high temperatures, they start quitting substantially earlier in the day. Among low-risk workers, we see a shape that is reminiscent of the figure on the left, but not nearly as strong. And so what's important is, as we think going forward, we're going to have to think about how the composition of workers is going to change. To link up those response functions that I was just showing you, we're going to link them up to projections of the future following methods developed in previous papers. And we're going to look at 33 different global climate models that have been downscaled to a very fine local resolution. What you see on the right is the distribution of daily average temperatures today. And what's important is that there's actually going to be a change in that distribution. And so we're going to see a larger number of extremely hot days and a smaller number of all other types of days, basically to everything to the left of 29 degrees C. Now, in particular, that distribution is impacting the population through this response function. And so understanding what happens at the hot end of the distribution is going to be key. Now, in terms of understanding that very far end of the distribution, we're using highly localized climate data, and that's a key innovation in the work that we're doing. So, as I was showing you in the beginning, we're setting regulations based on the DICE model, the FUND model, which at the time they were developed were really powerful, insightful innovations. But one challenge is that the DICE model is actually only one region. The fund model is 16 regions. And so in our work at the Climate Impact Lab, we've sort of asked, well, given that we have distributed computing today, which wasn't previously available, how would one break up the world? And so we actually break up the world into almost 25,000 regions. These are roughly the scale of a county. In the United States, they actually are counties. And so what we do is when we take these climate models in this high resolution reconstruction, you see on the left the projected impact on high-risk workers, and on the right, the projected impact on low-risk workers in RCP 8.5. That's a high emissions scenario by end of century. So we can do this reconstruction for these two different subsectors of the industry. But what's important is also understanding how the weights that are placed on the high risk versus the low risk workers, how many individuals are in each of those subpopulations. What we can tell you is that empirically, as populations become wealthier, there's a large structural transition that occurs where people move towards work that is contained indoors. And we can also tell you that the underlying climate does not appear to influence that transition. And so we, didn't come in with a strong prior about what would happen if the climate changes, whether or not that would force workers indoors. It turns out we don't see a very strong empirical pattern that suggests that that's occurring. So what we're going to do is we're going to instead allow the workforce composition to evolve as we go forward based primarily on projected income. So here you see a map of what our estimates are for the share of high-risk workers in each country today. This is based on labor force surveys. And as we move into the future, based on the SSP scenarios, we project a reduction in the number of individuals who are working outdoors or in other high-risk environments. When we take those projections and then we combine them with these baseline response functions that we recovered from the data, we're able to then sort of re-weight what the average individual would be experiencing in the future as the climate moves forward. So here what I'm showing you is the average response to a 37, a very hot degree day, a 37-degree day today, given the current workforce composition in each country. And then as we project forward into the future, we actually see that the impact of hotter days declines, and that is largely due to increasing wealth, increasing incomes, causing more workers to shift from the high-risk sub-industry to the low-risk sub-industry. Overall, taking into account the change in the worker composition and changes in the climate, this is a map of the projected impact of warming in 2100 in all these 25,000 locations for the high emissions scenario. Now, what we can do is we can add up all those minutes across all workers that are projected to be working at that point in time and ask what is the cost to the global economy. So the orange line is the projected number of minutes lost per worker per day going forward in RCP 8.5 if you were to freeze the global workforce composition in the high and low risk ratios that are currently observed around the world. The green line is showing what happens when we cause those workforce compositions to transition from being dominated by the high-risk population, high-risk workers in many low-income countries to low-risk workers as incomes rise. And so you see there are some benefits of that type of transition. The other thing to note is that the change in the minutes worked per day sounds like a fairly small number. So for example, once we've accounted for this type of structural transition, we think we're losing about 4 minutes per worker per day. But one thing to remember is when we think about monetizing this, incomes are rising and a few minutes lost per day add up over time. So we do a very careful job trying to calculate the overall economic cost of the immiseration that those worked minutes represent, right? So it's not just those 4 minutes you're losing, but it's the value of all of the time that people are working exposed to thermal temperatures. And here are two projections for RCP 4.5, which is a moderate emission scenario, and RCP 8.5, which is a high emission scenario. So we see by end of century, a fairly large fraction of global GDP is lost in terms of utility of the workers. So it's around 1.5% by end of century, and it's about 0.25% by end of century in in 8.5, and in the moderate emission scenario, it's roughly 0.25%. Now, those numbers I was just showing you don't tell us what the optimal willingness to pay what the willingness to pay is of today's society to avert those damages. To do that, we need to compute the social cost of carbon, which requires computing what is the marginal cost of a marginal emissions pulse. To do that, we take all of our simulations from the different climate models. And for each climate model, we have an estimate of the damages that are caused to the labor force. And we also have an estimate of what global mean temperature is realized in each one of those climate models. So each dot here represents essentially a summation of all those 25,000 regions in a single potential realization of the future. When we plot them out like this, you can see, when we plot them out, sorry, my slide deck seems to have been cut off partway through. What I can tell you, I have my slides right next to me here. I will just tell you in words what happens. We are able to then just project these damages into the future, and we have essentially a damage function that is this quadratic function that's changing over time. And then what we do is we use a single dimension climate model to think about what a single impulse of emissions will cause in terms of damages moving into the future. When we compute essentially what is the partial social cost to the labor force through its disamenity on the global workforce, we estimate that for a discount rate of roughly, well, if you're at a discount rate of 2% in a high emission scenario, it's roughly $10 per ton in terms of the value of the disamenity. For a 2.5% discount rate, it's roughly $6, and for a 3% discount rate, it's roughly $4. Now those numbers decline to roughly half that value, so it's roughly $5, $3, and $2 at those discount rates if we have a low emission scenario. It's okay, Claudia. Oh, sorry. It's okay. This is the end of the talk. So I think the key message is that it's roughly, the SEC is on the scale of $5 to $10, depending on your assumptions about the discount rate and depending on whether or not we are in a moderate or a high emission scenario. There is, in this sector, evidence that we benefit substantially from reducing emissions because you have a lower SEC in our CP 4.5. And so just to recap, we have sort of tried to construct the largest comprehensive sample of worker labor supply, and we run regressions, which we can then interpret in terms of the disutility that individuals experience. We use those in projections of the future and accounting for adaptation, estimate, and partial SEC of labor disamenity, that's roughly $5 to $10. And with that, I apologize that somehow we lost some of the final slides and transcription. But hopefully there will be a working paper circulating soon so you can all see the details.
Great, thanks very much indeed, Phil. So, very interesting, very ambitious indeed. Can I just ask a clarifying question? Right at the beginning of the talk, you showed us a sample of countries for which you've got data, which was, quite a smallish subset. You're basically working from that sample and using that's it, thanks, right. So you're using the estimates from this sample and extrapolating them to the whole world, is that right?
Yes, so what we do is we basically, along with many, so we're trying to estimate the shape of the response that you would get if you had data in any one of these locations, conditional on baseline incomes, workforce composition, and baseline climate. And so that's the general pattern of how we work at the Climate Impact Lab. We do this for each sector, trying to collect as much data as is available. What's sort of the key assumptions are, for example, that a high-risk worker in a location in India suffers relatively similar disamenity of work as a high-risk worker in one of the other locations that has a similar income and for which we are basically using India as a proxy. And so, of course, there are some assumptions there, but we think it's important that we try to represent those populations that have not been historically sampled with data as best we can. Yeah, right, absolutely. But for looking at Africa, for example, which is obviously going to be severely impacted by climate change, and are there income levels in India which are comparable to some of the lower income levels in Africa? I guess there are in some regions, right? Yeah, roughly half. And so actually in the paper, we have a distribution where you can think about the coverage you get in terms of how much overlap there is between samples. And as incomes in Africa increase, they will begin to look much more like many places in modern day India, if they were started out lower income than India. Yeah.
Okay. Yeah, I see. Thanks. Okay. Don't seem to have any questions in the Q&A on this, but I noticed there's a couple of questions came up for Jisung after we had finished with Jisung's presentation. Jisung, are you still there?
I am, and I also have a question for Paul, so we can do either.
Well, why don't you go on with talk to Sol, and then we'll move on to some of the questions for you if we've got time.
Sure. So first of all, Herculean data lift, but as we've all come to expect from Climate Lab, the Impact Lab. So I have no idea. Well, I don't have a clear sense of how you would empirically operationalize this, but wondering whether there's any way to account for the fact that self-employed workers may have a different level of flexibility to quit their work during the day relative to others. I was recently looking at some survey data in the US that suggested something like 60% of American workers have to be on site, like during regular business hours, basically no matter what. And so I'm just trying to think about how, whether there's a way to augment what again is an incredibly rich analysis with something about how your ability to retire from a day's work may be constrained due to labor market practices. Does that make sense?
Yeah, so I think your point is a very good one. So there may be individuals who are constrained. They can't quit early. They can't stop early. And so first of all, that would have an impact on our estimates. What it would say is that, like, when it gets really hot, if I'm constrained and can't quit early, I'm going to keep working. And so in a sense, we are underestimating the disamenity because there are a bunch of people who can't signal how unhappy they are through the act of quitting early. So in some sense, this is like a conservative estimate. Part of what you're also describing might be one reason why the low risk response is relatively flat, right? Those individuals may be in work environments where they're closely supervised, and it's very difficult for them to quit early as well. So I think your intuition is potentially consistent with the evidence, and also, suggests a way in which we might be underestimating these costs.
Yeah, interesting. Jisung, let me just pick up one question for you, which came in after I closed the box. Are injuries from poor air quality, e.g. asthma attacks, distinguishable in the data from other heat-related injuries?
Great question. Something we're hoping to look at in more detail, which is the air quality injury link. We haven't done that yet. I guess the question here is more concerned about disentangling the potential high correlation between temperature and at least ozone and some other air pollutants. That's a great point. We haven't done that yet. We should certainly look at that. I mean, yeah, I'll stop there. We should look at that.
Okay, thanks. Well, we've got 1 minute left, so we're pretty much right on time. So let me just thank the three presenters very much indeed. You've heard some real cutting edge presentations there. About 10 years back, I was on the IPCC, and I was the actually coordinating lead author for the chapter of the IPCC report, last one, on adaptation to climate change. I have to say there was no work around at all at that time of the quality of the work we just heard, regrettably. I'd have been very happy if we had papers like the ones you just listened to available at that time. And they will, of course, be available for the next IPCC report. So I hope it will be based on some much better academic analysis of the impact of climate change and how people can adapt to it. So thank you very much indeed for tuning in. The next session starts at in 15 minutes from now, just actually 14 minutes from now. But thank you very much, everybody. And thank you, Raj, to the presenters as well for three really fascinating talks. Very, very high quality talks indeed. Thank you very much.